When presented with the function 5x squared and the task of finding its first derivative, most people resort to the familiar power rule. For a function of the form x raised to the nth power multiplied by some constant a, the derivative is always the original power n times the constant a times x raised to the original power minus 1. Most people state this rule as multiply the function by the original exponent and then lower the exponent by 1. This allows us to quickly evaluate the first derivative of 5x squared as 10x, which is obtained by multiplying the constant 5 by the original power 2 and then lowering the exponent from 2 to 1. We can take the first derivative of this result to obtain the second derivative of the original function, which is 10, using the power rule. But how do we take the derivative of this result to obtain the third derivative of the original function? Instead of the power rule, we use what is called the constant rule, which states that for any function that is equal to a constant c, the first derivative is always 0. This makes sense when you recall that a function equal to a constant is a horizontal line, and any horizontal line has a slope of 0 at every point, making the derivative 0 at every x coordinate. The derivative of 10 and the third derivative of 5x squared is therefore 0. The power rule applies to quotients as well. For example, consider the function 4 over x squared. This can also be written as 4 times x raised to the minus 2 power. The first derivative of this function using the power rule is minus 2, the original exponent on x, times the constant 4 times x raised to the minus 3 power, which is 1 less than the original power. This can be rewritten as minus 8 over x cubed. Now let's consider the function 3x to the fourth minus 2 times x squared plus 5x minus 7. To find the first derivative of this function, we use something called the sum rule. A function h of x, for example, that can be written as a sum of two other functions, such as f of x plus g of x, has a derivative that is the derivative of f of x plus the derivative of g of x. The sum rule tells us that the derivative of a sum is the sum of the derivative of each term evaluated individually. The derivative of our example is therefore 12x cubed minus 4x plus 5. The second derivative can be evaluated easily using the sum, power, and constant rules as 36x squared minus 4. It is helpful to know the rules for evaluating the derivative of trigonometric functions such as sine x and cosine x and other transcendental functions such as the natural log of x and the natural exponential e to the x. The first derivative of the trigonometric function sine x is cosine x, and the first derivative of cosine x is negative sine x. Using these rules, it is easy to determine the second derivative of sine x to be negative sine x, and the second derivative of cosine x to be negative cosine x. You can take higher derivatives over and over again until you exhaust yourself. For the transcendental function natural log of x, the first derivative is 1 over x. The second derivative can be found by using the power rule on this result. For the function e to the x, the first derivative is easy to remember because it is the same as the function itself. Higher derivatives are all the same. Let's combine these rules with the sum and power rules to find the successive derivatives of the function 3x cubed plus sine x minus e to the x. The first derivative is 9x squared plus cosine x minus e to the x. The second derivative is 18x minus sine x minus e to the x. Notice how the sum rule lets us take the derivative of each term in the sum individually without considering the other terms. Let's say we want to evaluate the first derivative of the function sine x divided by x squared. The first thing I'm going to do is write this as the product x raised to the negative second power times sine x. The power rule would apply to finding the derivative of the first term by itself, and the rules for trigonometric functions would apply to finding the derivative of the second term alone. But what do we do when two functions are multiplied like this and no single rule seems to apply? We need a new rule. The product rule states that for a product of functions, let's call them g and h, the derivative of the product is the first function times the derivative of the second function plus the second function times the derivative of the first. This gives us a way to evaluate the derivative of our example function in which x to the minus 2 is the first function g and sine x is the second function h. The first derivative is the first function x raised to the minus 2 power times the derivative of the second function, which is cosine x, plus the second function sine x times the derivative of the first function, which is minus 2 times x to the minus 3 power. Rearranging this to make it look a bit nicer, we have cosine x over x squared minus 2 sine x over x cubed. As another example, consider the function sine x times cosine x. In this case, sine x is the first function g, and cosine x is the second function h. The first derivative is the first function, sine x, times the derivative of the second function, negative sine x, plus the second function, cosine x, times the derivative of the first function, cosine x. The result, when rearranged to look more appealing, is cosine squared x minus sine squared x. Now we want to consider the function y of x equal to e to the negative 5x squared. Our rules tell us how to find the derivative of the natural exponential e to the x and how to find the derivative of negative 5x squared, but they don't tell us how to do so when the functions are combined in this manner. We can make some progress by defining a new function u as a function of x to be negative 5x squared, the entire contents of the exponent in the original function y. We can then write the function y as a function of this new function, which is in turn a function of x. This gives e to the u as a function of x. This new function, y of u, is called a composite function. It is a function of a function. This helps because we can evaluate the derivative of e to the u with respect to u. We just need a new rule for using this result to find the derivative of the original function y with respect to x. The rule that helps us here is called the chain rule. If a function y of x is written as a composite function, y is a function of another function, such as u of x, then the derivative of the original function with respect to x, dy dx, is the derivative of y with respect to u times the derivative of u with respect to x. Returning to our example function, the derivative of y with respect to u is e to the u. The derivative of u with respect to x is minus 10x. According to the chain rule, the derivative of the original function with respect to x is the product of dy du and du dx. We have these quantities already, therefore the derivative is e to the u power times negative 10x. Rewriting this more nicely, we have negative 10x e to the u. Substituting u back in, we have negative 10x times e to the negative 5x squared. Let's consider the more complicated function f of x equal to sine squared 2 pi x over a, where a is some constant. We might be able to evaluate the derivative of this function by using the chain rule if we define the function u of x to be 2 pi x over a, which is the argument to sine squared. This allows us to write f as a function of u equal to sine squared u. This, however, is not differentiable using any of the rules we have talked about. Going even further, we can define another function w as a function of u to be sine of u. Then we have f of w equal to w squared. This is a composite function nested 2 levels deep. F is a function of w, which is a function of u, which is a function of x. Despite the complexity, the chain rule still applies. The derivative with respect to x of the original function is equal to df dw times dw du times du dx. Each layer of the composite function has its own derivative. Evaluating each derivative in turn, we obtain the derivative of f with respect to w is 2 times w. The derivative of w with respect to u is cosine u. The derivative of u with respect to x is 2 pi over a. Putting all this together, the first derivative of f of x is 2w times cosine u times 2 pi over a. Combining 2w with 2 pi over a, we obtain 4 pi over a times w times cosine u. Substituting w gives 4 pi over a times sine u times cosine u, and finally, substituting for u gives 4 pi over a times sine of 2 pi x over a times cosine of 2 pi x over a. Just about any function relevant to physical chemistry can be differentiated using a combination of the rules and procedures presented in this microlecture. And that's rules for finding derivatives.